Imagine managing a team of 5 specialized AI agents: a researcher, a writer, a fact-checker, a designer, and an editor, all deployed on a single project. You immediately face an architectural problem. How do these discrete entities share information without talking over one another? The coordination pattern you choose dictates the entire system's speed, its accuracy, its security, and how many API tokens it burns through. Making the right choice yields a scalable production tool. Making the wrong choice results in a hallucinating system that leaks sensitive data and bankrupts its creators. The oldest and most intuitive approach is the Blackboard pattern. It functions like a single, universally shared workspace where all agents can read and write. 5 individual nodes feed into a massive central data block. Because agents process the entire board every turn, token costs scale exponentially. Simultaneously pulling identical, unfiltered data exposes a critical security flaw. Without access control, sensitive data cannot be hidden. To solve for privacy, developers often swing to the opposite extreme, the message passing pattern. This relies exclusively on point-to-point direct communication between individual agents. Nodes send distinct data packets directly to one another along independent paths. Token usage drops since agents only process specifically addressed data. But as tasks multiply, routing complexity takes over. Determining who sends what to whom creates a tangled, chaotic web nearly impossible to debug. Absolute transparency burns your token budget, and absolute privacy destroys your routing logic. A complex system requires a completely different orchestration method to scale. That method is the supervisor with scooped workers. This is the enterprise-grade architecture used in actual production systems. This animated diagram shows a large, central hub node dispatching distinct, fragmented pieces of a whole data block outward to smaller perimeter nodes. A central coordinator analyzes the incoming task and delegates strictly restricted data contexts to each specialist. The perimeter nodes process their specific fragment and return new output back to the hub. This scoped access guarantees security and minimizes token waste. Centralizing orchestration while strictly isolating worker context allows the system to solve both scalability and security at once. The supervisor pattern doesn't run itself. It sits inside an operational environment driven by a rigorous 4-stage pipeline that manages the end-to-end conversation flow. Stage 1 is ingestion. The system parses metadata, timestamps the query, and loads the user's historical session checkpoint. This flowchart shows Stage 2, context assembly. A large volume of unstructured data passes sequentially through 4 distinct filtering gates: select, compress, write, and isolate, outputting a single, highly condensed block of context. Stage 3 is the agent loop. The language model executes that assembled context, invokes necessary external tools, and loops until it produces a final response. This animated diagram shows Stage 4, compaction. A capacity bar fills up to a marked 70% line. Once that threshold is crossed, a critical housekeeping protocol triggers, instantly shrinking a stack of older data blocks down into a single thin layer. During compaction, older messages are summarized, and new facts are instantly extracted into long-term episodic and procedural memory. Without this 4-stage pipeline running constantly in the background, even the most advanced supervisor architecture will quickly drown in its own memory overload. Let's run a practical scenario. A student asks a multi-agent Python tutoring system why their code keeps crashing. In stages 1 and 2, the supervisor isolates the user's raw code specifically for the syntax checker agent, while keeping that same code entirely hidden from the code executor agent. In the Stage 3 loop, specialized worker agents analyze the bug, run tests, and write the fix. They then pass the validated code back to the supervisor. Finally, in Stage 4, the system identifies the student's persistent coding errors and extracts them into procedural memory. The system learns the student's habits to improve tomorrow's session, well before it ever hits a token limit. We explored the massive mathematical expenses of the Blackboard pattern, the tangled routing of message passing, and the secure efficiency of the supervisor pipeline. Mastering this specific architectural evolution and pipeline is the definitive blueprint for controlling speed, enforcing security, and managing cost in any AI enterprise.